Same concepts of heterogeneous equilibria apply to solubility. For these, we can define a special equilibrium constant that is going to be basically the product of the ion concentrations. It's not going to include the solid itself because, again, as we said, solids does not contribute to the expression of the equilibrium constant. And that is special equilibrium constant is called the solubility product constant. And the form of the solubility product constant is going to be different according to the formula of the salt. So for this example right here, magnesium fluoride, if you try to set up the expression for the equilibrium constant or the solubility product constant, KSP, it should be the concentration of magnesium times the concentration of fluoride to the power 2, which is the molar coefficient of the ion, right? So for something like calcium phosphate, KSP is going to equal the concentration of calcium to the power 3 times the concentration of phosphate to the power 2, right? So you have to pay attention to the molar coefficient of the ions when you set up the expression for the solubility product constant for any salt. And that solubility product constant will give you very valuable information about the solubility of an ionic solid. Because if you mix the ions of any solid in a ratio that makes the reaction quotient, the product of their concentration, smaller than the KSP of the combination, that means that the solution is unsaturated, so they will not form a precipitate. But if the reaction quotient equals the solubility product constant, that's a saturated solution. It's not gonna form any precipitates, but it's not gonna be able to dissolve any more ions. If the reaction quotient is larger than the solubility product constant for the sample, that's a supersaturated solution, which means the equilibrium will shift to the left-hand side and a precipitate of the salt will form. The concentrations we have in the expression for the solubility product constant are actually molar solubilities, which are different than the gram solubilities that you most of the time find for different salts. So whenever you do calculations in this context, you will have to convert the gram solubility of any salt to molar solubility first before you use these molar solubilities to get the concentrations of the ions and use the ion concentration to get the value of the KSP of the compound. And you can go backward as well. You start from the KSP value, you get the concentration of the ions, A and B, and then these are going to give you the molar solubility of the whole compound, the molarity, and you have to convert that to gram per liter of the salt. This is one example here. The gram solubility for the salt is this value, and it's asking to calculate the KSP for the salt. So you have to start by writing a balanced equation for the solution of the salt, which is going to give you calcium ions plus sulfate ions. And based on this, the solubility product constant for that salt should be equal to the calcium ions multiplied times the sulfate ions. So the first step is convert the solubility from grams, 0.67 grams per liter, to moles using the molar mass of the substance. So 1 mole is 136.2 grams. This is going to give you 4.9 times 10 to negative 3 molar. In solution, all this amount will dissolve to make the same number of moles of calcium and the same number of moles of sulfate. So KSP is going to equal concentration of calcium, which is 4.9 times 10 to negative 3 times the concentration of sulfate, which is the same number. So it's going to equal 2.4 times 10 to negative 5. Predict whether a precipitate will form when you mix ions of a certain salt. So you're mixing barium chloride with potassium sulfate. The only combination in this mixture that might be insoluble is barium with sulfate, because the other combination is a salt of a group 1 element, potassium, which is always soluble, right? So, and it gives you the equation here for the solubility of barium sulfate with a KSB value of this value right here. And it's asking, if you mix these concentrations here, are you expecting a precipitate to form or not? You calculate the reaction quotient for this type of reaction and compare it to the solubility product constant for the salt. It's gonna form a precipitate only if the reaction quotient is larger than KSP. So in order to calculate the reaction quotient is going to be the concentration of barium times the concentration of sulfate, right? So we need to find the molar concentration of sulfate and the molar concentration of barium. Remember, you cannot use the concentrations directly from the given information here, because what will happen when you mix these two solutions is that the concentration will get diluted, because you start from 200 mils and you end up with the sum of both volumes. So you will need to calculate the number of moles of each ion. Moles of sulfate is going to equal the volume in liter times molarity. So that is going to give you the number of moles of sulfate, which should equal 4.8 times 10 to negative 3 mole. And then to find the concentration, the molarity concentration for this ion, you will divide moles by total volume in liter. So it's going to be 4.8 times 10 to negative 3 mole divided by total volume is the sum of both volumes, which is going to be 800 milliliters or 0.8 liters. That is going to give you a concentration of 6 times 10 to negative 3 molar. Same thing for barium. Moles of barium will equal the volume of barium 200. Convert them to liter first, then multiply them times molarity. That gives you the number of moles. You will calculate the concentration by dividing moles of barium by the total volume. So it's going to be 8 times 10 to negative 4 mole divided by 0.8 liter, which is going to give you 1 times 10 to negative 3 molar. And that is going to give us a Q of the reaction, or a reaction quotient, that equals the product of the concentration of barium times the concentration of sulfate, 6 times 10 to negative 3, which is going to equal 6 times 10 to negative 6, which is, as you can see, is significantly larger than the KSP for the salt, which is just 1.1 times 10 to negative 10. So you basically should expect, since Q is significantly larger than equilibrium constant, it means that a precipitate will form, because the reaction will have to go to the left-hand side to decrease the product of the ions to make the reaction quotient lower down to the value of the equilibrium constant, or the KSP value. If you put a higher concentration of a common ion to your reaction, it's going to decrease the solubility of the salt. And that is a direct result of Le Chatelier's principle. Because if you, for example, increase the amount of silver ions in solution, the equilibrium will shift backward, forming more of the precipitate, or decreasing the solubility of the salt. So, for example, if we calculate the solubility for silver chloride in a regular solution, an X amount of silver will get dissolved, and the same number of moles of chloride will get dissolved. So KSP equals the concentration of silver times the concentration of chloride, which is X square, is gonna equal 1.6 times 10 to negative 10, which means concentration equals the square root of the KSP, which should give you 1.3 times 10 to negative 5 molar, which is the maximum concentration that you can dissolve of the silver chloride salt. So that's the maximum molarity, the maximum solubility in molar concentration of the salt. And if you want to express it in grams per liter, you just multiply times the molar mass of silver chloride, 143.4 grams per mole. And that gives you the gram solubility as 1.8 times 10 to negative 3 gram per liter. As we said, if you increase the concentration of one of the ions, is gonna shift the equilibrium to the direction that offsets the increase that happens. So for example, if we put silver chloride ions in combination with that much of silver nitrate ions, the silver nitrate ions is 100% soluble, which will mean that one is going to produce the same number of moles of silver and the same number of moles of nitrate. You will have an S amount of silver from the silver chloride equilibrium, an S amount of chloride, and you will have also that amount of silver coming from the solution of silver nitrate. So at equilibrium, the concentration of silver is going to be the sum of the concentrations that comes from silver nitrate plus the concentrations that comes from silver chloride. If you substitute for these values in the KSP expression for silver chloride, KSP value is going to equal the concentration of silver times the concentration of chloride. And we will make an approximation to make the calculation slightly easier by assuming that S has to be significantly smaller in magnitude in comparison to the amount of silver that comes from silver nitrate. That will make our expression become this formula right here, and that will make the solubility of silver chloride have this value right here. Or if you want to express it in grams, you will be simply multiplying this times the molar mass of silver chloride per 1 mole, and it's going to give you 3.6 times 10 to negative 6 gram per liter. And just to compare it to the pure salt had a solubility of 1.8 times 10 to negative 3 gram per liter. Just to see, adding silver nitrate, significantly decrease the solubility of the pure salt from this value right here to this value right here.